enjoy the entertainment and then pay attention to the technicals.
You want me to put a break in?
Sure, that's fine.
Okay, so here's the lecture.
All right, so today we're going to start by talking about steelmaking in a little bit more depth with some focus on the modern methods. And then, as time permits, we'll get into some other subjects. So, steelmaking is a bit, like, we could talk about hot processing and heat treatments and forging and all that without really talking about steelmaking. But I feel like we need to spend some time on steelmaking because it's sort of the foundation upon which we build everything else. So even though I'm not a steel mill metallurgist, I'm very interested in what happens at my suppliers and how they're doing their work because the output of their process is the feedstock for my process. So I need to know what I'm receiving, what I should be receiving, what's typical, not typical, and then that drives how I'm going to conduct the forging process later. So we're going to talk a bit about steelmaking. We're not going to go through all the intricacies of steelmaking here. I have supplied a video that we'll put online. Dr. Metzloff will help us do that, which is actually about 2 hours worth of some steel mill metallurgists actually giving a class at Scott Forge on steelmaking in more detail. And they go into some of the chemistry and alloying and so on. We're going to talk only about that just a little bit briefly and then get more into some of the solidification parts of that have more to do with what we're getting in the raw material that's coming into the forge shop. But we're going to start with what is steel, right? So just at its most basic, steel is an alloy of iron and carbon, and generally we consider the carbon content not to exceed 2%. In industrial practice, you find that it doesn't usually go over 1%, but there are some exceptions. We can put lots of other things in steel. They can be other metallic elements or non-metallic elements, and we've got lots to choose from, and they give us all different kinds of properties, depending on what we put in and how much we do put in there. To get to steel from iron ore, or from raw material, let's say it that way, we have two typical methods today. And we talked a little bit, just very briefly, on some historical methods, and time permits we can get into those later. But the two common methods today are either taking scrap metal and melting it down, or by taking iron ore and refining it into iron and then steel. So to refine iron from iron ore, the method used is a blast furnace. You take iron ore, you put it into a tower, a hollow tower essentially that's multiple stories tall, probably between 3 and 5 stories tall, and you would pour iron ore into it, and then you pour some limestone into it, and then you pour some coke into it, and you alternate those materials going up the stack. And at the bottom of the stack you would have huge, enormous blowers. Sometimes you might even have additional burners down there. But what's happening is, as you look at what's going on within the stack, within the column, you're getting carbon from the coke, which is basically sort of pre-burned coal. You're getting carbon, which is being absorbed by the iron ore and is reacting with the oxygen. You're pulling the oxygen off, and you're being left with iron. But the iron is now absorbing excess carbon, so you get a very high carbon, essentially cast iron. And all of this liquid metal is trickling down through this big tower and collecting at the bottom. And at the bottom, there's a way to what's called tap the furnace, and you can tap out the liquid metal and pour it into what a special railroad car called a torpedo car, and that allows you to transfer liquid metal from one structure to another place in the steel mill called a blast furnace, where you would now blast oxygen through the liquid metal, drive out all that carbon that you picked up. You'd be left then with iron, and now you can take that liquid iron and add your alloying elements to it and so on to produce whatever it was you're interested in. So that method used to be the primary way of getting steel. The blast furnace itself was invented in the late 1800s, and that technology was perfected and utilized very widely for the first half of the 1900s. And then we got to the point where we could have electricity as a source of melting rather than having to use solid fuel for melting. And we also had lots of scrap metal available. And so the technique was developed to take scrap metal and use what's called an electric arc furnace. This uses 3 very large graphite rods called electrodes, and you strike an arc between the electrodes and this container filled with scrap metal, and you melt the metal down. So that's kind of nice in that you're able to recycle a lot of material. So iron and steel are probably the most recycled material we have in the entire world. It doesn't get a lot of attention because aluminum and plastic and things like that get a little bit more attention in the common media, but your cars, any old piece of iron can be easily recycled, and it is. There's a market for that. There's scrap yards, that specialize in that, and there's a whole industry now that's built around that. So the steel making industry in general, you'll find that you actually by volume or by tonnage, you have more produced by the electric arc furnace method, where you're recycling old steel, than by making it from iron ore and making new steel. Now, there's still a market for both products, so both are still used. But for purposes of the industrial forging world, most of it is made, in fact, all that I'm aware of, is made by recycling old metal going through the electric arc process. Here's a schematic of what that looks like. You have a container called a furnace. You have 3 electrodes. You don't have to have 3 electrodes, but that's the most common setup. And you have your, what would start off as just big chunks of scrap metal. So it could be turnings, it could be crushed cars, it could be chunks of large material left over from what Step Forge does, combination of all of those things. They put it in the furnace, and they strike the arc, and they melt the material. Now, the steel mill is going to pay attention to the composition of the scrap that they're using, because there may be some alloying elements in that scrap that they want. And so that's a good thing. It means they don't have to add as much sort of pure alloy later on. So they pay attention to the scrap. The other thing they have to watch out for when it comes to managing scrap is things they don't want, in particular things that are radioactive. So within our world, we use radioactive isotopes for all sorts of really legitimate, useful things, medical treatments, things like that. If those end up in the steelmaking scrap, that's a real problem, and because you'll end up with some residual radioactive steel bar, right? So every steel mill that I've ever been to has basically a giant Geiger counter that you can drive a huge truck through to check the incoming raw material, their raw material, and they also do the same thing leaving their facility with the finished goods. Now, there was a kind of a notable failure of that system in about 2008, where Timken, a very large steel producer in northwest Ohio, received some radioactive scrap that they did not detect. It was some isotope of something medical related, was in a container, like say a refrigerator or a freezer or something, and it was shielded from the Geiger counters. They didn't realize it was there. They used the material, and then on the way out, they found that they had a radioactive truckload of steel going out, which was obviously a problem, so they had to stop. They couldn't supply that to the customer. But not only was that a problem, but they actually had to take this furnace completely out of service and tear out the refractory lining, because they had just gone and melted radioactive material in it, so the entire furnace was contaminated. It shut down the mill for some period of time. That happened to be when there was such a high demand for steel that Timken's customers had to wait about 9 months to get steel from them. So it was a big deal with that.
Was that a cobalt-60 source or something? Or?
I'm not sure the actual
It's
source,
X-rays though.
but something like that.
Yeah, it was
it wasn't
gamma rays.
Yeah, I mean, it wasn't like military type weapons material. This was stuff that's used in the civilian world for legitimate purposes, but it got into their raw material stream. Yeah.
How often do the electrodes degrade? I know they're not touching the mill, but can carbon content get added to the steel?
Yes, they can. Yes, and the electrodes are sort of continually eroding. They're graphite, and so they are in fact adding carbon to the liquid bath. The way these are constructed is there's a threaded hole at the top, and so you'll have a new electrode that has a mating threaded stud, essentially, that's machined onto it, and they can just thread them in from the top, and so they can just continually cycle through. I don't know what the actual life is of an electrode, but they're not small. The ones I've seen they're probably 16 to 20 inches in diameter and 8 or 10 feet long. They're pretty massive. Those are kind of interesting just a quick side note, from a materials general materials engineering standpoint, those have to be constructed and created in such a way to maximize the flow of electricity. So it's not like, it's graphite like your pencil, but not like your pencil, because it has to be, have, you know, directionality to the properties in there. I don't know how they get that, I just know that's important to that application.
Also, these are huge. This is not a small thing. So they could be 100 tons, in some cases,
Yeah.
50 tons
Yeah.
in that furnace. And it's a shallow pool, so these are big in diameter. They're like bigger than the room in some cases, in diameter, like the width of one.
They're pretty good size.
Yeah.
You know, depends on.
Depends on the
Yeah,
site.
most of the ones that I've seen are 50 tons, but there are bigger ones.
Yeah.
There are some bigger ones. And there is at least one that I know of that runs a single electrode instead of 3, and it is, I think, a bigger
Some Charter.
diameter. What?
Charter steel.
Okay.
Charter
That's
steel is a
different
single
one.
electrode. It's like this big around.
Yeah, there's one in Pennsylvania, ArcelorMittal Steel that has one, which is theirs is a big
It's
DC powered
DC,
furnace.
yeah.
Yeah, so there's variations on the design, but, you know, they have to be deep because you start off with stuff that takes up a lot of space, because, you know, you've got big chunks and that, so it's not, you know, as you melt it, of course, the metal, you know, settles down and occupies less volume, but when you first load it up, it's, you know, all these different weird shapes that don't nest together really well. So you have to have a big container to start off with.
It's the loudest thing ever.
Best way I can describe this, if you ever get a chance to visit a steel mill, absolutely take the opportunity. And if they'll let you stand out here when they're melting, do that too. And it's like, if you've ever gone to the fireworks and they get to the grand finale, it's like that, except that you're right next to it. So it sort of shakes you from the inside out. It's pretty cool. You can't see what's going on because all that's contained. It wouldn't be safe otherwise, you know. So you don't see any of that, but you can hear it, and it's just amazing. And it's interesting. It's loudest when they first start because there's a lot of arcing between the electrodes and the bits of metal that are sticking out. Once they get a lot of it melted, then the sound quiets down considerably. But it's a very impressive thing to see. Okay, so in steelmaking, we just talked about melting. That's the first step. The second step is refining. Refining is removing the things that we don't want. We have liquid metals, so we have the opportunity for chemistry to happen. And in that, you've got several things that we don't want in there. Phosphorus and sulfur in particular are problematic for most applications, so those are removed. They do that by having a chemically active material called slag, which tends to sit on the top of the bath of liquid metal, and then they'll use techniques to stir that liquid metal so that the slag and the steel can interact with one another. You can pull out the things that you don't want. Carbon is removed by blowing oxygen through there. Now, of course, one of the students here just asked about the pickup of carbon from the graphite electrodes, which is definitely a carbon source, so you may have more carbon than you want, so you're going to get rid of that by blowing oxygen through there. So we get rid of everything we don't want, and now we are going to need to put in what we do want. So if we're making a plain carbon steel, there's not much to be added. A little bit of manganese, and that's probably about it. Maybe a little carbon, because you've probably taken the bath of liquid metal to nearly zero carbon, and then you'll add in what you need, because carbon is really cheap and it's simple to add. But other things like nickel, chrome, molybdenum, vanadium, those are things that if they're present in the scrap, they're probably going to stay in your liquid metal. So you test it to see how much you have after you get your metal melted, and then you determine how much you need to add. So you add that in to get to the composition that you want. Now, in practice, it's not typically check once, add what you need, and you're done. It's usually do that a few times because the steel mills are trying to work to usually fairly narrow ranges on chemistry. And it's important that they get it right to satisfy their customers. So there's multiple checks and little tweaks throughout the process. There are some things that are added in right at the very end, right before they empty the liquid metal into the ingot mold. These are elements which, if they added them earlier, would actually burn off or react with something else and wouldn't end up being in the steel. So the two that I've highlighted here are sulfur and calcium. I just said we take sulfur out and we do. We typically don't want a lot of sulfur, but there are some exceptions. So if you're in one of those exceptions, the mill has methods for putting the sulfur back in to get to the target level. Calcium is an additive that's used once in a while to help manage the shape of sulfides, which can affect mechanical properties. And again, it's one of those, calcium we know is a pretty reactive metal, so we've got to put it in at the end of the process, or it's not going to be really there to do anything for us. Okay, so one other very important step of steel making, especially when you're making large cross-section ingots for the forging industry, is to remove dissolved gases. And there's two ways that you can do this. First way is to take this container of liquid metal that you have, and we call that a ladle. And I should just point out, that it may not have been clear earlier, melting is done in the furnace, and a lot of steel mills will then transfer that liquid metal from the furnace to a new container called a ladle. They don't all do that, but many of them do. Once you're in the ladle, you can do whatever you need to do with it, and one of the reasons for doing that is because now that frees up your furnace to melt another batch of metal. So the mills that are set up that way tend to be fairly high output. You're in the ladle, you've made your alloying additions, you're nearly done, but you need to make sure you get rid of dissolved gases. So that's going to be any of the gases that we have in our atmosphere, oxygen, nitrogen, hydrogen. The way that's done is to take that ladle, and it's quite large, and you put it into a container that you can put a lid on and actually draw a vacuum. And while the ladle's in the container, you've got a mechanism to stir the material so that you can expose all that liquid metal to that vacuum environment. And from a forging standpoint, the element, the gas that I'm most interested in getting rid of is hydrogen. Hydrogen has the ability to cause internal cracking in a finished forging. We can talk about why that happens more in another lecture or later in this one if there's time. But we really don't want hydrogen in steel. It's a very negative element. So we do degassing to get rid of hydrogen. So this is called tank degassing, when you put the ladle inside of a big container. And then once you're done with that, you very quickly remove it from that container, and then you're going to go into the teaming process, which we'll touch on here in a moment. The other way of doing this is, if you don't have a tank or you don't want to use a tank method, is to take your ingot mold, put your ingot mold inside of a container, which is under vacuum, and then actually pour the metal through usually a little aluminum plug. So the liquid metal hits the aluminum, melts through the aluminum, and is now entering a vacuum environment. And that stream of liquid metal, which is typically just a few inches in diameter, will essentially atomize because it's being exposed to this vacuum environment, and it allows for a really rapid and complete removal of dissolved gases from the liquid metal. There are, I know of at least one shop here in the United States that does that. I know there are others around the world that do that. That's a technique that's used widely in very, very large ingot production.
Is the first one just to keep it warm while you're doing all the...
Here?
Yeah.
So, right, so here you've got, often you'll have a secondary set of electrodes that are used for, a little bit of reheating so you don't get too cold.
Okay. So you melt in the big arc furnace, you put it into this container, and then they put the lid on, and those electrodes allow it to stay warm while you're doing it. Because we're at like, what, 3,000 degrees now?
About 3,000 degrees, yeah.
So your refractories are usually only good to about, what, 32, 3,400?
I'm not sure what the upper limits are.
I think it's like 3,400 if it's magnesia or something
Sure,
like that.
yeah.
And so you're right at the edge of what the refractory can do itself.
Yeah. And the refractories break down and have to be replaced, repaired. That's a normal part of the steel making process. These things have to be refurbished on a regular basis.
And you don't want that little plug in the bottom to fail.
So here they've got, frequently they'll have some sort of a porous plug where they can bubble argon through. That helps with agitation when they're trying to get rid of dissolved gases. So one of the mills that we do business with, during their degassing process, they can use both argon and an induction stirring to really get a lot of agitation going.
They actually make a plug for the induction furnaces that we can put in. And I'm pretty close to putting one in one of our furnaces to where you could melt steel and then you can bubble argon through it and stir it and degas it and all that good stuff.
Okay, so now we're at the point where we have the liquid metal, we've got all the composition correct, we've got the gas removed, and so now we need to take it from the ladle and put it into a mold. And that process of going from the ladle to the mold is called teaming. It would be called casting if we were making a shaped component, but we call it teaming in the world of steel. So we have liquid metal, now we have some options what we can do with it. We can make an ingot, or we can make what's called a continuous cast bloom or billet. Most of what we deal with at Scott Forge is ingots. We do purchase some continuous cast product. I want to talk a little bit about continuous cast here because I neglected to put a good illustration in it. But continuous cast method starts with a copper mold that has a bottom that's held in place by a big hydraulic cylinder. And they don't pour the metal directly into the mold, they'll pour the metal into a giant tub called a tun dish. The tun dish can have different configurations and different number of openings. The mill that we deal with mostly uses a tun dish that has 3 openings. So that means they can fill 3 molds at once. But the molds, as I said, they're not just big containers like a big ice cube tray. It's a bottomless mold that has a temporary bottom held in place with a hydraulic cylinder. And so the copper, you'll pour metal into the copper mold. The copper is water cooled, so it chills that metal on the outside pretty rapidly. And the hydraulic cylinder will lower at a slow rate, allowing that metal to continue to chill on the outside. You get that cylinder down to a certain point, and it is actually lowered completely out of the way, and the metal shape that you're making is actually forced to bend through a very large arc until it's laying horizontally. Now, the machinery that does this is usually several stories tall. The advantage to this is that that tun dish can be always kept full of liquid metal. So you bring a ladle over, you put the ladle and you fill up the tun dish, and then you switch that ladle out, you bring a new ladle in before the tun dish ever gets empty. So you always have a continuous stream of metal coming out of this system. This is really advantageous because you have no interruption in casting, so it's good for really high volume stuff. You also don't have you don't have a defined top and bottom of an ingot, which like you would with ingot making, which we'll talk about more here in a few minutes. You don't have that. So the only thing you have to really worry about is the transition between one alloy and another alloy, and they have ways of tracking that. And so they can, as that metal is bending through the big arc, once it's down horizontal and reached a point where it's fully solidified, they'll typically set up automated torches and just cut out what they don't need. That just goes right back into the melt process and is remelted. So continuous casting is an extremely efficient way to produce a material. It's not used very much for really large cross sections. So the 2 mills in the United States that can make relatively large cross sections, one is ArcelorMittal located in Steelton, Pennsylvania. They do a cross section that's about 14 by 26 inches. And in Timken, in Canton, Ohio, they do about 18 by 26 or 18 by 28. Those cross sections are large enough that an open die forge shop like Scott Forge can use those to make some smaller products. Most of the continuous cast mills that are out there, and I would say that most of the shops that I talked about where they're using the electric arc method are continuous cast shops. They're making smaller cross sections that are going to go into something that's going to be rolled as opposed to forged. So round bar, structural iron, you can make I-beams, coils, flat stock, rebar. All of those products are processed through rolling, and so the incoming feedstock lends itself well to being made by a continuous cast process. In forging, we often need very large cross sections, and so we're kind of limited with what we can produce from continuous cast product, which is why we use so much ingot. We'll talk about that and the reasons for that here in a little bit. So then the other thing you can do, though, when you have liquid metals, you can turn it into powder. And that's a very small segment of the steelmaking industry, but I know Dr. Metzloff's got plans to discuss that in more detail later in the course. But metal powder definitely has its uses, especially when you're dealing with very high alloy components. If you make them into metal powder and then take that powder and bond it into a solid form, it's often easier to process than if you tried to make a large static cast component. Because if you do that, you tend to get a lot of chemical segregation, which can make processing very difficult, make it difficult to have uniformity of properties and performance characteristics. So there are companies that specialize in that method of making specialty materials.
There's some really cool steels, stainless steel. It's got 2.3% carbon. Now, it's not technically a steel, but it's done by powdered metal, and they make blades for things, and I have a piece of that. It turns out to be very air hardening and cracks if you look at it the wrong way, but
I believe it.
it's super wear resistant.
Yeah, sure. And we'll talk about why that all is in later lectures.
Yeah.
But yeah, that's some interesting stuff. So getting back just to ingots, ingots are available in just a huge variety of sizes and shapes. The smaller ones may be 10 inches in diameter, and the biggest ones I know of are pushing 700 tons. The biggest ones that I've seen personally are probably about 69 inches in diameter. So that's 69 inches. So I'm 6 feet tall, 72 inches. So that's an ingot laying down on its side that's almost as big around as I am tall. Those are some pretty big pieces of steel. I've seen pictures of one that was nearly 700 tons, 12 feet in diameter. So it's absolutely huge. Ingots are typically configured, they're poured in such a manner that the metal comes into the ingot mold at the bottom, which Dr. Mensah mentioned that earlier. The reason for doing that is it results in a material which is cleaner. We'll talk about why in a minute. Ingots are really well suited where you need smaller quantities or you need a big single piece. They're good for where somebody's going to do, they just do a lot of variety. So at Scott Forge we make a whole lot of different things for a lot of different customers with a lot of different alloys. So the steel mill is able to meet our needs by being very versatile by making ingots, as opposed to when we buy continuous cast material, we typically have to buy 3 heats of the same thing, all in the same size. So we have to have a lot of orders for just a narrow group of things to make that worth our while to do that. We kind of covered this slide already, so I'll just leave it up there for just a minute and then I'm going to move on. And then powder we kind of touched on as well. There's some neat things that you can do with powder outside the industrial world. In fact, I had some samples here last week of there was images that were forged into a little thing that looked like a steel quilt, and that was all done with powder metal processing. Okay, so here we're getting to actually look at the images of teaming and ingots. Here we have the ladle. What they're showing here is a method called top pouring, where the ladle is emptied into the top of the ingot mold. This technique is not used in the forging world very much. It used to be very common, it used to be the only way of doing things, but what's been found is that if we pour into a funnel here called a trumpet and let the metal flow horizontally and then come in at the bottom, the way that liquid metal flows is not very turbulent. It's called lamellar is the term that's used. It's very lamellar, and that's good because you don't churn in stuff you don't want. So these molds are all poured in the open atmosphere. So you think about, we just spent a bunch of time trying to get dissolved gases out. Now if I pour into the top of this stuff all hits the bottom. It's like filling up a cup at the faucet when you turn the faucet on. Everything is all churning. You got constant air bubbles. Well, the same thing's going to happen here. So you're going to put all kinds of oxygen and hydrogen and nitrogen, everything all back into your metal when you do that. That's not what we want in the forging world. So this is the method that our suppliers are using. Here you can see what that looks like in a shot from a real steel mill. And then here you can see what this looks like, the setup they would use before they actually fill molds. And then here you can see some molds that are already full of steel, and the ingots are protruding up from the top. They've taken off a section of this mold called a hot top, which is basically, like the guys in casting would consider that a riser. And we'll talk about why that's important to us in the forging world here in a moment. Any questions before I go on?
That ladle sits right on top of that that sprue, you think?
It does, but it's not really taking the weight. It's all supported by an overhead crane.
Sure, but
Yeah, what they'll do.
sealed there.
Yeah, so what they'll do is they'll have a fiber refractory ring.
Gasket.
Yeah, gasket, and so that they can just lower that down so it just barely touches. And a lot of steel mills will actually have argon piped into that ring so that you have an additional barrier between the atmosphere and the liquid metal. So, we do have a little break time planned here. Do anybody need to take a break? Questions? If not, we'll just keep going. All right. So, now we're going to talk about solidification. We've got the steel, it's been liquefied, it's been processed, now it's in our mold. And so now, this is the part that starts to begin to really affect me as a forging person. I've got liquid metal that's going to a solid, and I'm interested in what happens when we do that. It's the process of freezing. We have chemistry happening here. We've got chemical segregation occurring. We have metal that solidifies at one temperature, but the ingot doesn't solidify all at once. It's a giant ingot, and it takes a while to get all that heat out. So solidification is happening slowly over time. And what that means is that there's an opportunity for what was at one time a uniform composition. When the steel mill melted it, put it in their ladle, chemistry was uniform. It was all liquid, it was evenly distributed. But the metal gets into the mold, and now it starts to solidify, and it starts to become non-uniform in composition. Does anybody know why that is? Yeah. Were you raising your hand to answer?
Yeah.
Okay.
But you can include more things at higher temperatures, so as it cools, it kind of pushes them out toward the higher temperature areas.
Sure. Yeah, it does. That's exactly what's happening. There's temperature, there's a relationship between temperature and how much can be dissolved. Yeah. I saw another hand.
Yeah, it was just the solubility, whatever
Okay.
is dissolved in there, as it cools down and pushes it out and creates a little layer.
Mm-hmm. Yep. So we can show what you guys both just answered by taking a look at our phase diagram. If we look up here, we have all liquid, and this is the liquid to solid this line right there, right? And we can see with increasing carbon content, this line changes dramatically, right? So if you think about having the metal that first hits that mold wall and is first to solidify, there's going to be a tendency to push carbon in particular away from that solid-liquid interface, right? And so, that's what this diagram predicts. And the longer we are liquid, the higher the carbon content would be, because there's more time for that carbon to be pushed away from the interface. So what we find in practice is that the composition of an ingot actually is quite variable depending on where you check it. How close are you to the top or bottom, or where are you through the cross section? So I had one of my former interns do a study on this, because that has application to me. You think about having variable composition, you now have variable response to heat treat, variable, at least the potential for variable mechanical properties. Those are all things that are important to me, making a finished good for a customer. So I had this study done where I took ingots of similar cross-section from several different suppliers, and we took the ingots, or in one case this had been forged out to a large square cross-section, a big billet, and we cut slices out of the ingot at the top, middle, mid-height, and at the bottom, and then we evaluated the composition at positions 5 equally spaced positions from the surface to the center. And I have all the data of all the different elements that we looked at. I'm not going to show all of that, but just to show you the concept, if we look at the element molybdenum, we can see that we started off at near or just under 0.2 in this particular case, and as we move from the surface towards the center, it starts to bounce all over. And we see that different mills had, overall we had kind of the same behavior. It was lower near the surface, higher near the center. That was a consistent behavior across the board, but the actual amounts varied depending on the mill, how much they started with, So this was for molybdenum, which is actually a fairly large atomic radius element, one that we wouldn't expect to do a lot of segregating. When you look at carbon, you see even more dramatic behavior because carbon is a much smaller atomic radius. It's a lot easier for it to move around. So this is quite significant because if I'm making a finished forging and then I'm going to be checking the mechanical properties, do I check out near the surface? Do I check in the center? Do I check somewhere in between? That's all going to make a difference in the, or at least have the potential to make a difference to the results that I get and how well I do at meeting my customers' expectations. This one does show the summary of the carbon content. So we were dealing with material that was nominally a 4140, so approximately 40 carbon material. And we could see that it really quickly changed. All the way out the center line, we had some carbon that was up in excess of 55. That's a huge difference. You think about the effect of carbon on hardenability, which is something that we'll cover in another lecture, but some of you may have been exposed to it already. To increase your carbon by 0.15%, that's a lot. That's a big difference. And that's not because the mill made any changes, in additives, just because the carbon was mobile and could move throughout the cross-section during solidification. So I don't have any real control over this as a forging guy, and I can't really change it. Once the ingot is solid, it's solid, and I can't really redistribute those elements. They're in there. But the steelmaker has some things that they can do to adjust that a little bit. You can look at and try to adjust the temperature at which you pour the metal. The higher you are, the longer it's going to take for that metal to solidify, and the more time there is for this to happen. So if you can keep your what they call teaming temperature, the temperature at which you're pouring it, if you keep that low, you're going to minimize that condition. Now, of course, you have to balance that because if you're too cold, then it'll freeze off before the metal fills the ingot completely, and you'll have a scrap ingot. So just as you would if you were making a shaped casting, you've got to have enough heat to get the mold filled all the way. But you want to minimize how hot that is. Another thing is they can look at and work on changing the shapes of the molds to try to extract heat more rapidly. So many molds are just smooth, straight sided. And that's fine, there's plenty of application for that, they work great. But when you get to larger cross sections, most often what you see are molds that are fluted. And the output, the ingot actually has flutes in it, and the mold wall has flutes. And it's designed to increase the surface area so that you can get heat out of that ingot a little bit more rapidly and, again, try to mitigate the severity of the chemical segregation. Here's an illustration of what that could look like if you took an ingot, sliced it down the middle from top to bottom, and then did a very aggressive etch, what we would call a macro etch. You can see what almost looks like the grain flow that we talked about last week, except there's not been any plastic deformation down here. This is just the result of solidification. And you can see how the chemistry is, because of differences in chemistry, you get this different response to the etching that allows us to see where the segregation is at. And so they have different terms for this, A and B and so on. At the very top, we see a big cavity in the hot top. That's normal. That would be the equivalent of a shrinkage cavity in a riser in casting. That's pretty typical. If you want to learn more about this phenomenon, there's some papers that you can go find. It's something that's been studied quite a bit. There are ways of predicting it. There's different tools out there that will allow you to try to understand better what's happening. I kind of rely on my suppliers to have that expertise and to use that expertise to give me the best product available, that I can get. But because of the sizes that we're dealing with, we know this is going to be present, and we can't eliminate it through normal steel making processes where you're just taking a single melting step. You can, and we'll talk about it later, you can use other techniques to try to reduce the severity of that, but that requires additional melting, additional energy and cost, so it's only done when it's absolutely necessary. we just talked about changes in composition, but I touched just very, very briefly on the fact that when you go from liquid to solid, there's a change in volume. Steel shrinks, so you end up with these shrinkage cavities. So the ingots that we receive all have holes in them, and they're oriented along the center line. And the terminology that's used in the forging world, we call that pipe. In the boundary world, that would be called a shrinkage cavity. It's the same thing. You have the last region to solidify. There's nothing there to fill the void, so you end up with a void. The hot top or riser is intended to minimize how severe that is, but we always have a certain amount of that present. So this is really very critical to me as a forging engineer, because I need to get rid of those holes. My customers have an expectation that those won't be there. It's one of the reasons they're coming to me for forgings. So I need to really understand the nature of those, and then how to use my processing to make them go away. And that will be getting into the discussion of forging and forging technique. Just to show you some of the options that are available when it comes to ingots and ingot configurations. This is from Elwood Quality Steels. This is our main supplier, but there certainly are other steel mills out there. They all use similar types of ingots. We have ingots which are cylindrical and what we call straight-sided or parallel. And these are available to us as either smooth or fluted, depending on the size. Another type that we get are what are called big end up ingots. And these are available as rectangles or as tapered cylinders. The difference is that, and we'll actually get into it in a minute, I'll show you some schematics, but these two solidify from the bottom to the top, where these two solidify pretty uniformly along the whole length. That is significant because if you do have some small bits of non-metallic material, something that's solidifying directionally gives you more time for those little bits to float to the top. The top is something that we're always going to cut off and discard. So the result is that these two give us a little bit cleaner material, something that, depending on our customers' non-destructive evaluation requirements, we may need to use to meet them. Typically, a customer would say, I need you to do an ultrasonic test on this, and I want it to meet something like, say, a 5/64 flat bottom hole, or a 1/16 of an inch flat bottom hole. The smaller that criteria, the cleaner we have to have the steel, and that drives what ingot configuration we're going to pick for their product. So in practice, what that looks like is if we have sort of modeled these two side by side, we just filled both of these up at the same time. Imagine, for example, that these were in the same system, so we poured the liquid metal down the trumpet right through here. One was tapered, one was straight-sided, so they filled up at the same time. And now we're starting right at the beginning. As we go through the solidification process, you can see change in temperature, and you can see that here the tapered ingot is solidifying more rapidly on the bottom than the straight-sided ingot. And when we get near the end, we can see that straight-sided ingot is solidifying here and here basically at the same time. That means that you're going to have some amount of piping or holes all the way down almost to the very bottom of the ingot, where in a tapered ingot, that condition will be limited and will be much closer to the top, and then you'll have much fewer of those holes throughout the body of the ingot. As we're solidifying, if we could imagine ourselves kind of at the, not quite the atomic level, but close to that, you're going to initially form a solid particle. That solid particle is called a dendrite, or a grain, but in the casting world we call it dendrites. And the dendrites will grow, and then they'll grow up at 90 degrees or at some angle. You'll get little arms coming off of them. Right? And so this is illustrating that growth process. And over time you'll get a whole bunch of them all connected together like this. So these are all solid, and then in here you've got some liquid. Eventually that liquid solidifies as well. So I showed earlier the segregation that we can measure throughout the cross-section of the ingot. We call that macro segregation. But if we had the right analytical tools, we could actually see that there's slight differences in composition between these dendrites and this remaining liquid as well. Yeah?
So in that Boothbird video, they talked about how with the original cast ingot, it was hard to forge like right away because all the dendrites were still intact.
Mhm.
If it has bigger crystals from the dendrites though, wouldn't that make it softer? And then when you break them up, it would...
Depends on what the dendrites are made out of.
So, so there's softer as in, if I'm gonna do a hardness test, right? And I can measure differences in hardness. But when we're talking about forging in response to deformation, that's a different quality.
Oh, okay.
All right, so if I have a very large grain or group of very large grains, that may have a tendency to want to separate along grain boundaries while I'm forging.
Oh, okay.
And so that's kind of what they were talking about there. You also have, in that particular material, you have very high carbon content, so you have iron carbides or iron complex carbides with, depending on what little alloying elements they put in there. And so the carbides may still be present at forging temperature. In fact, they are in that case. The carbides are pretty hard. They are actually physically hard. And so they're not going to deform in the same way that the surrounding iron matrix will. And so now you get a difference in what's called flow stresses. And so as you try to deform this, the carbide is maybe pushing through the softer iron matrix, perhaps creating some shear stresses at that interface,
Okay.
and resulting in a tendency for this to want to come apart during deformation. So in working on material like that, and I can give you similar examples from stuff that I deal with at work, the way in which you do deformation, how fast you deform the material, makes a big difference into whether or not it'll stay together or rip apart.
Cool, thanks.
Yeah.
You also gotta be careful with the really high carbon stuff, because if you get it too hot, you can have incipient melting of the,
Yeah.
and so, because that, you've got really high solute in those interdendritic regions.
Right here. So just exactly what we were talking about before. On the macro level, carbon is pushed to the last metal to solidify, but the same thing happens on the micro level. So this region here is going to have a lower melting temperature than this region here. So if in heating you get to a point where this area starts to melt, and then you go to forge that, it's going to tear, crack, crumble, right? Or let's say you get it to where you're not quite that hot, but you're close. And now you go through a forging process, and your forging operations, or rolling, I mean, it could be any kind of a deformation process, but that process is done with such aggressiveness that you actually get heating of the metal due to internal friction. We call that adiabatic heating. You can actually get to the point where you're going to cause this to reach a melting temperature, and you'll get grain boundary melting.
Okay.
So those are all things that we try to avoid. Any other questions before we move on? Good. Okay, so I think we touched a little bit on this last week, but we have, here's that cross-section showing the segregation in the macro edge. This is the ingot split from the top to the bottom. Here's a cross-section, a radial cross-section or a transverse cross-section. You can see the columnar orientation of the grains, right? And we can see other structures in these other, here we've got equiax and columnar together. That's another longitudinal section. So these are showing the as-cast structures. And I talked about last week the desire to change those as-cast structures into something different. Not only to close up the holes, which we see in the upper right, we've got that pipe in that one, but also to change the nature of those as-cast structures. So we need to understand those so that we can change them in a way that's going to give us the property benefits that we talked about last week. Before we do that, we want to touch on one other way of making steel. I mentioned remelting a few minutes ago. If we've got a really highly segregated material, one way that we can deal with that is to remelt the metal using a different process. So we just spent time talking about melting a big vat of metal, pouring it into a mold, letting it solidify. That's pretty basic stuff. We can take the output of that process, an ingot, and we can turn it essentially into a giant welding electrode. If anybody's had a chance to do any stick welding in particular, this is basically that, scaled up to a massive level. You take the ingot, you attach you weld a fixture to the end of it so that you can bring in a power source, and then you put it into a large water-cooled copper mold. And what happens is you strike an arc on the bottom between the ingot and the bottom of the mold. And it's exactly like welding in that you're melting from one end to the other, but that happens over a long period of time. So you melt and you solidify, and you are only ever left with a really small amount of liquid metal at any one time. This takes place over, an ingot that size might take a day, maybe 24 hours, 30 hours to go through this process. What's happening is the metal is melting kind of drop by drop off the bottom of the ingot. And in this particular process, in the electroslag process, there's a slag layer that liquid metal falls through, and that's chemically reactive, much like the slag that's used in the main steelmaking process. That slag is there to help remove any little bits of non-metallic material that may have been entrained during the primary steelmaking method. So this gives you a very clean steel, but because of the way in which you're remelting it, going from the top to the bottom, or excuse me, from the bottom to the top, and doing it very slowly, and doing it just a little bit at a time, you're able to get a much more uniform composition. So we use this process. Most of the time it's driven by the desire for very clean material, but it does give us the added benefit of having very reduced segregation. So we could use it for that reason in certain situations. There's a variation on this method that's called the vacuum arc remelting process. The setup is basically the same, except that rather than using a slag layer, the melting process is done under vacuum. That process is ideally suited to removing any extra dissolved gases that you may have picked up. So we see in our business that certain stainless grades are, say for example, precipitation hardening stainless grades are quite often remelted using the vacuum arc remelting process, or VAR, and we see other grades, duplex materials, some alloy steels are made by the electroslag remelting process. So they're all available to us by the single melt process or air melt process, but then the remelt process is kind of tailored to different grades based on what you need.
Yeah, titanium ingots, you may have to be done that way, right?
Yeah, actually, I think they're done by an even different process.
They go 4 or 3 times, they go through this process, going through bigger and bigger diameter electrodes.
Yeah, that's one way of doing it. I know we receive titanium ingots where you can see on the end faces, you can see the chips that they started with that are still there that haven't melted in completely. But I don't know when exactly when the process is for.
Where do you get them from?
titanium.
You get them from out west?
Some of them do come from out that way.
Yeah, so one of the guys that graduated from this program, the metallurgist out there, went and visited him.
Oh, yeah.
And watched this process. It's very, very cool. The problem is titanium, 3,500 degrees, so we're above our refractory temperatures. So you have to melt it in this, and you can't ever have a whole bunch of liquid because it's up against water-cooled copper.
Yeah.
So in order to get a uniform cross-section, then they forge these ingots out.
Oh, yeah.
So I saw the ingots that you guys
Yes.
receive.
I've seen some ingots. We had the biggest ingot that I ever saw in titanium was, I think, 40 by 53 by, I forget how long it was, but it weighed 45 or 50,000 pounds. What's really neat about titanium, though, if you ever come and visit me and I have a titanium ingot that you can see the grains on it oftentimes. And Alex and Kara, you guys probably saw that when you were out there. You can see the grains. Grains sometimes are this big. They're huge. And often titanium will have some oxide that's got some coloration to it, blue like these chairs, or green or gold. And so the grains are in these multicolored speckled spectrums on the surface of the ingots. They look really, really neat. But a grain that big, I mean, it's fantastic if you're making art, but other than that, it's not really good as an engineering material. So we got to change that. That's where the forging comes in. So I kind of touched on these next 2 slides already, so I'm going to just skip past them. This is a schematic of the ESR process, just showing the cross-section of the mold and how you get that drop-by-drop melting going on. So we touched on a lot of this already, that you get very clean steel this way, you can reduce chemical segregation. And the other big advantage is because the solidification is happening very directionally from the bottom to the top, you're able to eliminate the shrinkage cavities almost completely. You'll find some right at the very top because you still have the last little metal solidifies. To solidify is still going to go through a shrinkage process. Yeah,
How much are these ingots worth?
a lot.
Are they
So-
like the scale
so-
of 10 grand or?
Oh, way more than that.
Okay.
Right, so the average price of a piece of carbon or alloy steel in the, in the air melt condition is probably going to be, let's say alloy steel. Just, you know, it's going to probably run you around $1 a pound, maybe a little less. Something like this, if it's an alloy steel that's been remelted, maybe $2 or $3 a pound. But that's a pound. So if I'm buying an ingot that is 40,000 pounds, 50,000 pounds, or in some cases 70 or 80,000 pounds, we've got some parts that we make for one of our aerospace customers where we use basically the full product of a 76,000 pound ESR ingot. You know, and we get that out of Germany because there's nobody in the States that can make one that big. That's a lot of money, right? So you got to be really careful so that you don't mess it up. You know, I've dealt with ingots that were 100,000 pounds, for, you know, or $100,000 for one ingot, and that's you know, sort of stainless steel. You're talking about titanium, where you might quadruple that, maybe. You know, I don't know.
Yeah, we saw an ingot on the floor, it was 3 foot in diameter, maybe 30, 40 foot long, it's $1 million.
Yeah, you know, each material has its, of course, its own price, you know, depending on demand and all that. But yeah, when you get into big things, even if the per pound price is not much, they're big enough, it's still a lot of money. Yeah. Any other questions? All right. This is probably a good time to take a break. I've been talking for an hour, so you guys, I'm sure, are ready to do something different for a little bit. Just before we start this lecture, shameless plug for internship opportunities. Next Wednesday, there's a career fair over at Gordon Commons for engineering and technology folks. So I'll be there with one of the other people from Scott Forge. So please feel free to come by and see me. We can talk. We've got resumes. I'm definitely looking for students for summer and also for a co-op position for summer and fall next year. That's my shameless plug.
When is it? It's
It's on the 6th, next week,
6th,
on the
okay.
Wednesday. Yep.
So go by and see the Scott
Yeah,
Forge.
I'll have on my fancy jacket again, so you can't miss me.
It's also what, hopefully will allow us to have him come for the rest of the time, you know, if it's, or the angle is that they're angling for somebody, it's a win-win, you know, right? We get him to come talk and then you guys get a job.
Yeah, absolutely. Okay, so we're going to switch gears now, unless there's questions. I should ask, are there any questions over anything we've covered so far? We good? All right. So now we're going to talk about forging technique. We covered steel making, raw material. Let's talk about forging now. So in the world of forging, we have two different processes. One is called upsetting and one is called cogging. We're going to get into both of those. But before we do that, I want to talk about math. In the world of forging, math is important, but it's simple math. It's geometry. We're dealing a lot with volume calculations. We need to know, for example, a customer says, I want you to make whatever it is. They send us a drawing and say, make this for me. Well, we need to know how much metal it's going to require to make that. We have to have a certain amount of allowance for machining stock. We have to allow a certain amount of loss because we're going to have some oxidation. So we have to take what the customer wants, we have to add some additional onto that, and then we have to know, you know, how much is that? How much does that weigh? So that we can go and cut off the correct amount from our billet or our ingot or whatever it is that we're starting with. The other thing that's important and why we need math is because we need to know how much we have changed the cross-sectional area of our starting material to our final part. Remember I said that we're trying to do two things when we're forging, more than two things, but two things, especially at the beginning of the forging process. One is we're trying to close up the shrinkage cavities that exist within the ingot. And we're also trying to reform and reshape and break up those grains that are, in the case of titanium, as big as a quarter or whatever, that are not good for engineering applications. We need to reform those. So to do that, we have to have a certain amount of deformation. And we talk about that in the forging world as reduction of area, the change in cross-sectional area from the original section to the final section. Now, everything that Scott Forge produces, and this is fairly common within the industry, is going to have a minimum of 3 to 1 reduction of area. So the final cross-section will be at least 3 times smaller than the starting cross-section. That's arrived at through lots and lots of years of experience, and not just at Scott Forge, but all around the industry, that amount of reduction is the minimum that's required to change the microstructure from the cast structure to the what we call the wrought structure, and also to close up those shrinkage cavities. Now we're going to talk about in probably fairly great detail how you can work to the mathematical requirements on paper without actually accomplishing the goal that you have. So I can create a forging, for example, that has 6 to 1 reduction in it, but I still haven't closed up the shrinkage cavities, and maybe I haven't developed a good wrought structure either. So the method by which we apply that deformation is very, very important. Math, and I'm not going to go through it here because it's fairly straightforward, but you can calculate how to, say if I have a cylinder of some starting diameter and I want to make a longer cylinder of a smaller diameter, if I know the final size, I can figure out what length of some larger diameter I need, because we know that volume doesn't change when you forge other than for whatever you lose to your oxide, right? It's not like I can compress the metal like I could a gas. I can't compress it. Its volume is going to be the same. I'm just redistributing where that volume is. So if I know what the customer wants, I can do the geometry to figure out what I need to start with to satisfy both my customer's need and the mathematical requirements for the reduction variable. I'm going to, when we do upsetting, I just mentioned that term when we started this section. So upsetting is the deformation that we do when we take an ingot and we forge it along its axis. We shorten it along its long axis. Okay? So if the ingot was, let's just say the ingot was 8 feet long, and I start by shortening it to 4 feet, that is an upsetting process, and I have achieved 2 to 1 reduction. So I've shortened it by half. If I take that ingot, maybe it's, again, 8 feet long, and I stretch it out, let's say it had a cross-section of, let's just say it had a cross-section of 400 inches, and I reduce its cross-section to 200 inches, I've stretched it out substantially, and I've, again, achieved a reduction of 2 to 1. The cross-section has changed. Now, sometimes in the forging world, we need to do both things before we're done. We might do both upsetting and drawing out. And so then if we're going to report to our customer the amount of reduction we have when we use multiple steps like that, we will actually multiply the two together. So if I have 2 to 1 upset and I have 2 to 1 drawing out, my reported mathematical reduction is 4 to 1. It's multiply rather than add.
So I'll put this PowerPoint, so I mean, it's hard to read on the screen. You probably won't be able to read it on the video. So I'll put this PowerPoint on Canvas.
Sure. Yeah, we can put all of them up there for those who want them.
Yeah, but so far I have.
This is, and again, these are just additional examples of how to do that. I expect that all of you took high school geometry at some point. Just as a side note, as an engineer, with all the math and physics that I ever took, high school geometry is what I actually use in my job. And it's for this, it's for calculating these things. So, just page 2 there. So, any questions on that? It's very straightforward math. I should be all comfortable with that. Okay, so I I talked about in the previous lecture the three types of ingots that we have. We have the cylindrical or straight-sided ingots. We have those that are rectangular and have the big end up. And then we have those that are remelting. And we talked about how they all have different solidification characteristics, different internal characteristics in terms of the level and severity of the shrinkage cavities. This is what a shrinkage cavity may look like if you cut into one without having done any deformation. You're going to see some holes, maybe a combination. In this case, we have holes and some cracking, right? And if we've properly forged this and eliminated this, we won't find any evidence of it. It doesn't show up when you do metallography. It doesn't show up if you do non-destructive evaluations like ultrasonic testing or magnetic particle testing. You've made it go completely away. Yeah?
Does it forge well to close?
It does.
Okay.
Yeah, that's exactly what happens. We don't use the term forge welding. We call it solid state welding, but it's the same thing, right? Solid phase welding. If you really are interested in solid phase welding and you want to learn more about it, there's a book called Solid Phase Welding in Metals by a guy named R.F. Tilecoat, out of print. If you want a copy, you can probably buy one for a lot of money from Rick Furr, because he typically tries to find them all and buy them and then sell them to blacksmiths for lots of money. But you can find them in libraries. You probably, the school may have one in the library. It's an excellent book.
We actually do have a really good library here.
Yeah.
Some of the books have been taken off campus and housed somewhere, so you gotta dig around. We had stuff going back to 1800s from all of the casting and all the forging and all that kind of stuff. We have, if you get a hold of them again, they're really cool to page through, but they're in some shoebox now somewhere off campus.
Some of those old books have been reprinted and are available for purchase or are even available online as Google Books for free. That particular one is not, I don't believe, but it's an excellent book if you're interested in that aspect of metallurgy. Pretty much anything that R.F. Tilecoat wrote is pretty good. He did a lot of stuff on industrial history, and he was pretty good.
We need to put a list of all your, what you say, like your sources here. We'll have to.
That one's mentioned. I've got slides in there. If you put all the slideshows on Canvas, there's I've cited
some references.
Yeah, I've got reference slides in there. So this book is there. Other books that are interesting from just a historical note are those that were written by a guy named Cyril Stanley Smith. And I don't have any of his stuff that I've drawn on particularly for these lectures, but again, if you are interested in that kind of thing, he's an excellent author to get a hold of. So back to shrinkage cavities. So here's an example of some shrinkage cavities that I found in some ingots. These were 24-inch diameter ingots, and they were straight-sided cylindrical ingots. And we had cut with a saw some of the metal off the ingot to make some other forging. So we had the remnant still in our inventory so we could make something else of it. So just walking along in our stockyard, I found a couple of these and just took pictures of them. So these are holes. These holes are about the diameter of a pen or a pencil. And they were, in this case, these were over 100 inches below the top. So imagine that that ingot is cast vertically. It was probably 130, 140 inches tall, and we're still seeing a hole the diameter of a pencil, 2/3 or more below the ingot top. Right? And this is typical. I could find this condition. This is normal. When I saw this, it wasn't surprised or shocked or concerned. This is normal to see inside the ingots that we deal with. Most of the time, we don't cut the ingots. We usually leave the ingots intact and forge them so that we don't have those exposed to the forging atmosphere. We'll talk about that more in a bit. But there are times when you can cut the ingot and make something out of it and have the remnant and still use it successfully. So that's what it looks like if you take a picture of it with your phone. This is what it looks like if you take a picture of it with an SEM. So remember I talked about how metal solidifies and it makes crystals, which we call dendrites. Well, here you can see a really excellent example of a three-dimensional view of a dendrite. There's several in here. You can see here's the main arm. In this case, we've got probably a main arm that's buried down here, and we've got secondary arms out here. And there's no liquid metal or anything else around this because this was the very last spot to solidify. So there is no other stuff there. So that dendrite is just kind of hanging out in free space. I have, and I forgot to bring it today, I actually have a chunk off of an ingot. It's the very, very bottom called the ingate, and it broke, and you can actually see see the dendrites without the aid of an SEM. They're big enough that they're just sticking up out of the surface of the fracture. And I've got that as one of my show and tell pieces, but I'll try to remember to bring it next week. So this is useful to us because if we're looking at a forging that's failed an inspection and we find that, that tells us that we didn't do the forging process properly. We never deformed this surface enough to get the forge welding or solid phase welding to occur, so we're left with these dendrites that never got deformed, and that's an indication of poor forging technique. So, in the world of forging, we use this term that I put in quotations called consolidation. Right? I want to be clear that we're not making the metal more dense. Right? Metal has a density, it's fixed, I can't change it. But what I can do is take holes which may exist, and if I forge it properly, I can collapse those holes and get them to be eliminated through a solid phase bonding process, or solid phase welding. We'll talk about that. So I've got included here a slide that is really important to us as a forging company. So when I teach this material to our staff at work, I really make a point to emphasize this, that this idea of 100% consolidation, that the idea that I've completely eliminated any of the shrinkage cavities is super important. And why is that important to me as a forging person? Or maybe I should say, why is that important to my customers?
Porosity is going to be a stress concentration point. It's going to cause failure.
That's right. That's the primary reason. It could lead to premature failure of the part. So we want to eliminate that. I like to say, when I give this lecture at work, if the customer wanted holes, they could go buy casting. So, and yeah, they can serve this as initiation sites for problems. Either, and some of those problems could occur either in later manufacturing steps or in service. It wouldn't necessarily have to be just in service that they can cause failure. So this solid phase welding, let's talk about that. What that is, it is of course the same mechanism that's used to make pattern welded steel, or lots of other things like those cell phones that I showed in my lecture last week. They're made by the same metallurgical process. But here we're not taking different alloys and combining them together in a solid piece. We're just taking a block and making the holes go away. There's other examples of solid phase welding that are used in industry. We've got, some of you may be familiar with friction welding, spot welding, explosion welding, if anybody's ever heard of that. If you haven't heard of that, you should look it up, it's pretty neat. They use that technique for bonding dissimilar metals together to make large plates where you've got maybe very corrosion resistant surface on one side and a very strong, but not so corrosion resistant on the other side. So maybe for making like a pressure vessel that's going to be used in a corrosive environment, could be one application for something like that. So we want to get bonding to occur. We really need two criteria to make this happen. We need to have perfectly clean surfaces, and we need to get those surfaces close together on the atomic level. We can have things that seem like they're close together. If I take two pieces of metal here and I touch them together, they're touching, but at the atomic level, they're really not touching very much. Just a couple little spots are actually touching if you're at the atomic level. So we need to get them close on the atomic level. So to do that, we're going to use our forging process. First, we have to make sure the surfaces are clean. If they're not clean, then we can't get any kind of bond to happen. This doesn't matter. It doesn't matter whether you're dealing with an ingot, you're trying to close it up, you're trying to make a forge welded knife or a sword, you're trying to friction weld something for an automotive application. All of these things require clean surfaces. In the world of forgings, we make sure that we achieve that clean surface criteria by leaving the ingots intact. That is, the mill sends us the full product of the ingot. They don't cut off the top or the bottom, even though we know that eventually that material is going to be discarded. we leave that intact.
Isn't that cool?
That is very cool.
This was in Loper's office
Oh, boy.
when he retired. This is, I don't exactly know, they somehow decanted an ingot, or it ran out and it was solidifying. And I don't have to touch the actual ingots themselves, it's kind of heavy. But get a really good idea of what the dendrites look. I think that's steel.
Yeah.
I think that's exactly what we're talking about.
I gotta say, that's a better show and tell piece than the one I have. So thank you for bringing that. That's cool. That's very cool.
Here's an S-swing hammer.
Oh, yeah.
Forge.
Sure, yeah, we can talk about that a little bit too. So we start with an ingot which is intact. The hot top and the bottom are left on it. And the reason for doing that, anybody know why? How do we do that? So I showed a picture of what happens when you cut them off a few minutes ago. I've stumped the class. I need a star chart, so like when I can ask questions and you guys don't answer, then I
You
get
guys eat
star.
corn on the cob? Okay. Gotta hold on to something, right?
Well, that's one reason,
That's
yeah.
one reason, yeah.
Yeah, that's one reason. It provides
See,
a
those
lot
little things
to-
you stick in the end?
Yeah.
Just leave the end of it on. Just leave the husk, the stalk on
Yeah,
there.
yeah. But that's not why we do it, even though that is a nice side benefit. That's not why we do it, yeah.
Is it because when you cut that hot top off, it's flat and clean?
Well, it would be if you sawed it off, it would flat and
Yeah.
clean, but that's, we're not, we don't need that at this point in the process. Alex?
When you cut it off, it allows the inside surface to oxidize,
That's right.
and it's not clean.
Right, so in the images I showed earlier, we had this nice clean surface on the outside, but you had this hole that's running down the length of the ingot. So if I take that and I heat that up, I'm gonna get an oxide layer formed on the inside. Now if I go to squeeze that and get it to bond, I have a contaminant material in there and I'll never get it to bond. So generally I'll leave the ingot fully intact. Those holes are present, but they're capped. So when I can heat it up and those holes, because they're capped, they formed in a vacuum to begin with, so there's no oxide on there to start with. So as long as I maintain the integrity of that vacuum, I can get it as hot as I want and nothing's gonna happen to it. And now I can start to deform it as long as I get the surfaces to impact with one another, then I can get bonded. But if I get some form of contaminant in there, whether it's iron oxide or something else, they're not gonna bond. So if I do have a situation like what I showed earlier, where I've taken an ingot and I've sectioned some of it off for something else, and now I want to make something new out of the remainder, I can take a welder, I can weld that hole closed to create a seal, and now I can go back and heat it and forge it, and so I can make it work, but most of the time it's more convenient to just have the entire ingot sent to us so we can forge it, and then as we go through the forging process, once we get the holes closed up, then we can cut off the material that we know we're going to discard and not compromise the interior part. So we just answered that, talked about that. All right, so we just talked about criteria number one, maintaining a clean surface. The second criteria is how do we get those two surfaces close on an atomic level? Well, we are going to do it through heat and pressure. You don't necessarily have to use those things. I can come up with examples where you could do it without heat, right? If I had surfaces of materials which are naturally non-oxidizing, so let's say I had gold, which is a noble metal, it doesn't oxidize. So if I took two pieces of gold and I pounded them together at room temperature, they would forge well. They would be bonded because the surfaces are clean, and it's a ductile, soft material, so it doesn't take a lot of deformation to get atomically close surfaces, and all of a sudden you've got a solid piece. So that's done in certain crafts. But in the world of industrial forging, the things that we're dealing with are so large and they're so strong at room temperature that that's not practical. So we use heat and pressure. We add heat to reduce the amount of pressure required to get the metal to be formed. So I just gave that example. If you ever do get a hold of that solid phase welding in metals book, there's several other examples that the author cites using metals like aluminum and copper, things that are fairly ductile at room temperature. So why? Why do we get bonding when this happens? And the answer shows up there automatically. It's because we have atoms that are moving across the interface that we've created. And initially, you just have a few atoms that move across that interface, but over time, you'll have actual diffusion taking place. So you heard Dr. Metzloff mention that in certain pattern welded materials where you have different carbon contents, you can end up with a fairly uniform carbon content over time due to the diffusion of carbon between high and low regions of carbon. It wants to even itself out. So you will get diffusion across interfaces, and that will enhance the bonding. Am I going too fast for anybody? Because I see some people that look like they're madly taking notes and they don't want to go faster than they can write. All right, good? So now we need to talk about how metal moves. So we've established the two criteria, perfectly clean surfaces and atomically close contact. To get the metal to be atomically close, we have to control how it moves. And that's really where we get into the fundamentals of forging. How do we exercise control? So I want to just say, last week I did a little forging demo. This week we're going to, you guys are going to get to do hands-on forging. I've got materials so you can all make a little project. And I said last week that it's all about control, and I talked about body mechanics and so on. In the industrial world, the same thing is true. We're interested in controlling what's going on. This is actually true beyond the world of forging. This is true for anybody that's dealing in metallurgy, and really probably engineering as a whole field. We're interested in controlling something so that we get a predictable outcome. This is certainly true in the world of metallurgy. And in the world of forging, the control that we want to exercise is over how metal moves. So if we understand how metal moves and we can control it, then we can be very intentional in how we go about eliminating the shrinkage cavities. So here's just a quick illustration of how those shrinkage cavities might be oriented in two different ingot cross-sections. So if I imagine this being a rectangular ingot, I'm looking at a transverse plane, or a round ingot, again, a transverse plane. Of course, I showed a picture of this, and we saw that it looked basically like that. You had a hole right in the center. If I were to section a rectangular ingot rather than a round hole, I would see something that's a bit more elliptical. Now, it might not be a giant hole like this. It might be a collection of small holes that are all kind of arranged in this way. Kind of just depends on a lot of different things. But you're going to have holes that are going to have some orientation relative to the original casting or the original ingot. I showed this image before. You can see here that you kind of have this collection of holes here in the center, but there's more out here and out here. So you definitely have sort of a long axis to this cavity and a short axis to the cavity. Here's the image I showed earlier where we do have just the round holes from the straight-sided ingot. So metal moves in a certain way depending on a bunch of different factors. One is how much metal are you trying to move at one time? How much area is in contact with, in our case, the dies of the press or the hammer, and where can that metal go? We talked last week when we were doing the forging demo what happens, why it's so much harder to move metal that's thin versus metal that's thick. Where can the metal go? How much resistance is there? That's going to be a function of temperature. It's going to be a function of friction. It may be a function of the specific type of material and what material characteristics it has. And then how much power do you have available? Your hammer, your press, whatever you're using to deliver force is going to have some amount of power. So all these things taken together were presented to me by a blacksmith named Clifton Ralph. He worked in steel mills in Gary, Indiana, and Clifton, I think he graduated high school, I'm not sure. He just died actually right before Christmas, but he worked for 30 years in the steel mills as a blacksmith doing industrial forge work with steam hammers, and then once he retired, he had his home blacksmith shop where he did some contract forging, and he did a lot of teaching. And this was how he presented the variables that go into making metal do what you want when you're forging. He used to say that forging is a little bit like hydraulics, but kind of in reverse. You're not dealing with fluids, you're dealing solids, but you're able to make those solids flow through deformation. Another way that I describe it to people who don't have an industrial background or point of reference is to say that forging is really nothing more than playing with Play-Doh. Anybody's ever made anything out of Play-Doh, when you're a little kid, or you have nieces and nephews that like to play with Play-Doh, it's exactly the same thing. And you can use Play-Doh or clay as a model if you're trying to understand what's going to happen. You could take, for example, 2 different colors of clay, roll them out with a rolling pin, stack them up in alternating layers, and then you could take some popsicle sticks, say, and press in different ways. And then you could take a piece of thin string and cut through this thing that you've made, and you can see how the layers change thickness and where they move. And that will be a very good model for what happens in a real forging situation. So we'll talk about these same variables, but expressed in a different way. The dies have width. There's friction between the die material and the workpiece. This is a variable that you can change by using lubricants or maybe changing die material. The workpiece temperature, how hot we get it, that's a function of usually chemistry, is going to dictate how hot it is. The depth of die penetration or drag. So this is how deep are we pushing into the metal in any one push. That's going to be a function of, again, power, tonnage, how much power is available to us, and workpiece temperature. The hotter something is, the softer it is, the easier it is to deform. So I'm going to stop for just a minute and ask if there's any questions. All right, so let's talk about how the metal actually moves. So for those that have been to a forge shop or have done a little forging before, you may already know some of this, but some of you may find this to be new. Only metal underneath, in our case the die, because we're not doing rolling, so we've got these 2 flat plates. So only metal directly underneath that plate, or that pair of plates or dies, moves, but it doesn't move evenly in all directions. And I'm going to show just a crude drawing of what I mean by that. If I put a little GoPro on the top die of my press, and it's looking straight down, and I bring the die down and I start to squeeze the metal, I'll see that this is where the die is at, and initially, before I do any deformation, my view looks like what I've got outlined in yellow. And after I start to do some deformation, the view changes to what I've shown here with this radius. And if I happen to be working on something that's a long square, and I'm standing looking at the end of it while they're doing that, I'll see basically the same thing. I've got this big radius. Okay? Now, what I don't see when we do this experiment is this. I don't see that the metal moves out and maintains a nice sharp corner. Right? In either view, I never ever see this. The metal won't do that. We'll only do this. Okay? So this is kind of important to understand why that happens. Here's another example of that. This is showing a tool being used to create an indentation, but what we can see is that this piece started off as a nice flat, and we drove the tool in, but the metal is not in contact with the tool along its entire profile. It actually is separated here. We've got this metal being pulled down this way. Right? What's happening is there's friction between, in this case, between that shaped tool or between the flat tools that we use at work. And I'll show that in this way. So all this area in yellow is the material, the volume that's affected by the friction between the workpiece and the dies. And this area in red is that which is not affected by friction. So when we forge, the metal that's not affected by friction is free to move, where this is trapped, at least for a period of time it's trapped. I'll show that with some laminated material. Here's some laminated material that I worked with at home. We've got multiple alloys, so they have different colors. And you can see that even though the cross-section is uniform, the individual layer thickness varies depending on where I was forging and how much force was applied as I did that process. So we can see that we have narrow narrow layers here, wide layers up here. This area was trapped by friction. This area was not, and so it was free to be compressed as the hammer came down. You can see there's another less clear section right here where that same thing happened. To show that from a different single alloy now, not a layered piece, this is a nickel alloy, and you're seeing the same effect, but this time illustrated by differences in grain size. Again, uniform in cross-section, but very fine grain through this area, and where we have the white speckles, we have larger grains. The metal was affected differently where we had no friction and we had friction. In this particular case, they brought the press down, and initially there would have been material that was not influenced by friction, and then eventually it was. The material on the top and bottom that was affected by friction kind of collided with one another, and then you did get some deformation of those regions. So I'm going to go back a slide here. This yellow area that I've labeled the dead zone, I often refer to this as a friction pyramid. And so the dimensions of that friction pyramid are a function of a few things. Yeah.
Okay, well, going back to the picture of the dead zone, so when you hit an object, right, so you would be hitting the top.
Yep.
So is it like an equal but opposite reaction for the bottom that clearly would happen on the bottom?
Right. So the bottom is the lower die, which is not in motion, but the top die is in motion. So you've got a force on the top, and you have that equal but opposite force on the bottom. So you're affecting both surfaces at the same time.
So should we assume that the properties are just like we're getting the same exact rate of flow on both sides?
Mm-hmm. Yep. That's a good question. Any others? So our friction pyramid, if we were going to try to describe it mathematically, we would say that the height of our friction pyramid is a function of how much metal is under the die. I'll show this schematically in a little bit. And that we would also say that metal that's inside our friction pyramid isn't going to move. It's trapped by friction. All that I illustrated in yellow, that's trapped by friction, unless I create a situation in which those two pyramids collide with one another. So that is to say, I have to do enough deformation to get that metal. Let me go back a minute here. It'll be clearer if I show it this way. I have to do enough deformation to push all this material in red out of the way before the metal that's highlighted here in yellow actually starts to deform. If I don't do enough of that, then these two positions don't ever intersect with one another. They'll never get deformed. Does that make sense? Okay. So we want to talk now about how do we make that happen. What are the forging conditions that we have? What goes on in those situations? So I mentioned a little bit back this term upsetting, where we take an ingot and we shorten its length, right? So that's one way of forging. And so because we do upsetting quite a bit as part of the forging process, we want to know, is that going to help us close up shrinkage cavities or not? And if it is going to, is there some critical parameter or critical amount that we need to have as a minimum for that to happen? So we're going to make a few assumptions in this little exercise. The first is that we have a die which is large enough to cover our workpiece during the entire upsetting process. The diameter, let's just assume, for example, that we have a cylinder. Let's say I have a 24-inch diameter cylinder. When I upset it, the diameter will increase because the length is decreasing, but the volume hasn't changed, right? So I need to, as part of the exercise, assume that I have tools that will cover that increased diameter through the entire operation. And we're also going to say that if we have a cylinder, instead of having a pyramid, we have a cone for our friction. So in this case, a friction column. So the height of our pyramid, or our cone, will change. In this case, it's going to increase because the amount of metal in contact with the die is increasing, the diameter is increasing, so therefore the height of the pyramid is also increasing as I move through the process. So this is a process that's typically done in one push. I'll take my starting piece, we'll put it between the dies, and we'll just push. And we'll just keep going until we reach the new height that we want. Now, the point at which our two cones intersect, if that happens, if we create a situation where they intersect, that's when we'll start to get the holes to collapse on one another and begin to bond. If we don't reach that sort of critical state, then they won't close up. We'll show that. Here's the initial start of our upset. We've done enough that we no longer have straight sides. We've got some radius, but at this point, my two dead zones are not touching one another. So if I happen to have some holes in here, which I probably do if I'm starting with an ingot, they haven't collapsed. They're moving around, but they're not actually collapsing on themselves. Now, if I keep going, and I get to a point where these two intersect, now I'll start to get those holes to collapse and begin to bond the surfaces together and eliminate the holes. So there was some research work that was done quite a while ago where they actually did an experiment where they took slugs of metal and they drilled holes in the center, capped the holes, and then did different amounts of upsetting, and then split that metal back open so they could see what would happen. And you can see here what they did. And initially, so like right here, this would be sort of the spot that I illustrated that's near the start. That hole is actually, if you look carefully, that hole is actually larger in diameter at this point than it was at this point. The hole is getting shorter, but it's getting larger in diameter. Now we're starting to get in this position that the hole is starting to collapse, but it hasn't actually completely eliminated any of it yet. Right here, though, we see that we've actually got some bonding happening. So this is the point at which those two friction pyramids, if you can imagine being there, are starting to intersect with one another. And we can continue the process and eliminate a bit more. Now, in this particular example, they were never able to completely eliminate the hole, but they got rid of most of it. This position here, where they first start to get the hole to go away, occurred when they had a 2-to-1 reduction in height or length. So they did, what we would say is, they did an upset of 2-to-1.
What is that? Why is it shaped? Is it a riser on the end or something?
I don't know why they chose that shape for the project. This type of form, if you made this form as a forging, you'd call that a flange. And that's a pretty common form to make if you were going to say have an axle flange or a gear with a stub shaft on it or something like that. So it's not an uncommon shape, and so maybe they were trying to mimic something that they would encounter that way.
If you're going to drill that out, the center had a hole in it or something like that, that would be fine, right?
It would, yeah, it would. So yes, if you, let's say you had a little bit left, you're going to drill that so it can go on a shaft. You're absolutely right. That would be fine. So from the standpoint of eliminating the hole, well, you didn't get it all by forging, but maybe by machining you can still get rid of it and still put the part in service.
Right, and you got the proper grain flow around the flange and around the outside edge.
Right. So what I was going to say was that could work provided you had enough deformation to still get your grains to the kind of form that you want for to have that wrought characteristic of the grain. I thought I saw another hand up at some point.
That was my question.
That was your question. So we do sometimes do that in the world of forging. Normally, at least in our company, we would do that as a salvage technique. We have the expectation of ourselves that we should be good enough at producing forgings that those are not going to be present. If they are, we may work with the customer and see if the job's going to receive a hole, can we put that hole in there to still make a part they can use. But it's not, in our case, it's not ever the first approach to making a part for the customer. I have read some older forging manuals where certain size, very large, solid forgings, it was used to be recommended that they be drilled and bored because they were so big that it was hard to get rid of those holes with the equipment that was available. But today, the large presses that are available, you should not have those holes present if you're doing your forge work properly and you understand the raw material that you're receiving. I mean, if something happens at the steel mill and all of a sudden you've got some really massive hole there that's not typical for what they supply, you may have a hard time getting it to close up. But under normal, typical conditions, you should understand the raw material that you're receiving. You should understand how to use the equipment you have to make that go away. Yeah.
Do the ingots you buy have like shrinkage pipe sizes like spec'd out? Does it have to be like within a certain range or?
So that's a good question, and the answer is no. Ingots are really hard to inspect because they have that as-cast grain structure. It's and they're also, the surfaces are usually pretty rough. So it'd be very difficult to do an inspection, an effective inspection on there that would be non-destructive.
Okay.
So it's pretty tough to do that. Yeah. So we don't have that as a purchasing criteria, but we would say if we know we've executed the forging process properly, and we have to make sure we have done that, and we still have major holes, then we'll be having a conversation with our supplier to say, hey, this is not typical behavior. Okay. So from the standpoint of just upsetting, what we would say is that if we're going to do an upset that's less than 50%, less than 2 to 1, we're likely going to actually see the holes increase in diameter. That may or may not be a problem, but we need to at least know that that's the behavior that's going to happen. If we're trying to ensure that we have properly closed up holes and we want to use some of those calculations I talked about earlier to validate that, then we need to make sure that if we're doing an upset that's less than 50% on an as-cast structure ingot that hasn't had any other forge work, then we're not really counting that towards meeting our goal of consolidating. We are deforming the metal. We may be doing things that are necessary to create the shape for our customer, but we don't want to consider that metal as that work as effective at closing up the holes. We need to do additional work beyond that to get that goal, to achieve that goal. Okay. Now, there's another process that we use in addition to upsetting. This is called cogging. So this is when we take an ingot and we start the initial deformation process. If we're not going to upset it, we're going to just start stretching it out. Or sometimes we'll do upsetting and then stretching out, but the stretching out part, the elongating part that we initially do, which is not done to create the final shaped forging, but it's just done to get that initial work in and really to close up the holes. The term that we use is called cogging. So we want to go back to the idea of our friction pyramid. How is that going to be affected by our cogging process? Well, I used the example of upsetting, and I said, well, imagine we have a plate or some tools that will cover the metal. No matter how much upset we do, then we know we can upset enough. At some point, we're going to get some closure of those cavities, and that's going to be good for us. When we're cogging, we often can't do that because the ingot has got length that's greater than the tools that we're working with. So now we have a new limitation, which is that at some point I'm going to push so far in with my tool that I'm going to create a really sharp step. And if I index my part forward and I push again, that sharp step that I create is actually going to fold over on the surface that I generated after the first push. We call that a lap. I tried to illustrate it a little bit when I did the forging demo last week. That's a quality problem that we can't have because that can effectively become a crack and serve as a stress concentrator for cracks during heat treatment or cracks during service. So our tools do limit how far we can push the metal, so we have to kind of take that into consideration. and I'm gonna jump to this illustration here. So if we imagine that we have friction pyramid, or pair of friction pyramids, for every push that we make, every adjacent push that we make. So this may be a little hard to imagine if you've not ever seen a video of this.
But I think I signed a video on that introduction to forging. If you guys actually watched that, they had kind of a bar kind of moving in and out. And there's, I think I put the BBC one on. You guys have the BBC one on there?
Is that the history coordinator?
It's like the British one. And
Yeah.
crazy music on it. If not, I'll put it up there. It's the cool one.
But
They show this.
so a forging press, you know, obviously the size of the tools scales with the size of the press, but what's common to see in the shop where I work are dies which are 30 inches wide. So if I have a 30-inch wide die and an ingot that's 140 inches long, I obviously have to make several different pushes down the length of the ingot to work it from one end to the other. And that's what I'm showing here. So if this is 30 inches, and this is 30 inches, and this is 30 inches, I've got these adjacent friction pyramids. And you can kind of see that as I go along, if I push enough, I'll get this to intersect with that, and we'll collapse this right there. And that's, of course, what we're looking for. But you can kind of see that I'm going to have a spot between these two where I'm not going to have deformation occurring at the center. And then I'll have some more deformation at the center, and then another spot that's open, and then another spot. And all the while, the surface on the outside is the same thickness. It makes it look like I'm working it uniformly on the outside, but on the inside, I'm not. You can show this picture here that I showed before. This shows that with the layered material. The regions that are worked at the center much more than adjacent regions which are not. So to overcome that, I have to do something really important. What I need to do is, as I forge down the length, I'll go from one end to the other, and then I'm going to rotate that ingot 90 degrees, and I'm going to make another pass. But the second pass that I make needs to be staggered from the first pass so that I hit those spots that I missed the first time around. Right? If I don't do that, if I don't offset or overlap those passes from one side to the next, I'll end up with regions along the center line that never really get worked, even though the part itself is a uniform dimension on the outside. So a really important question that arises now is how much overlap and how many passes do I need to make? If I'm trying to ensure that I give my customer a quality part, how do I know, as the person that's, in this case, the engineer maybe designing the forging process, or I'm actually the craftsman that's executing the part, how do I have confidence that I'm making the part good for the customer? Well, fortunately, somebody did some research on this at some point, and what we find is that there is a relationship between how much metal is under the die, which I've illustrated as W, the height of my workpiece, or the cross-section of the workpiece, and the amount of deformation that occurs along the center line. And that relationship is, if I have a die bite, which is 1/2 of my stock cross-section. So let's say I've got an ingot that's 20 inches in diameter, that means I would need 10 inches under the die. If I do that, and at the same time, I have a draft of 20% of my cross-section, so if that was 20 inches, 20% of that's going to be 4 inches, right? So in this illustration, if I have 10 inches under the die, and I deform it by 4 inches, my amount that's deformed at the center line will be 1/3 of my W. So in this case, W being 10, that would be about 3.5 inches is what I would actually get deformed at the center line for that example. Okay? So what that means is that if I'm trying to make some long, uniform shape, a bar, a billet, something of that sort, I'm going to need to do enough deformation meeting these criteria that I get 3 adjacent hits that all work the center, right? Otherwise, I'll be left with a gap somewhere along there. So what that means is I have to overlap or stagger from one pass to the next by 1/3 of whatever this is. And I mean, of course, if it's 1/3, then that means I have to make at least 3 passes. And now you can kind of see where the 3-to-1 rule of thumb comes from. It comes from this. You know, somewhere along the line, we have an animation in this, and I'm not sure when that shows up here. But before I leave that, are there questions on that? Because it is actually rather important. And I know we're getting short on time.
What's a good place to,
That's what I'm looking for.
maybe after that video or something?
Let me see here. There's still quite a bit. There's still quite a bit left here. So, yeah, there's still a fairly good chunk. I can stop there, I suppose, or I can keep going. What do you guys want to do?
I think if we're gonna get done with our demo and everything. So, just so you don't starve, I've got pizza and some other things, as well as some soda downstairs. We're going to run a little long today. If you do have some absolute thing you have to get to, you're going to miss out on the forging, but there may be some other opportunities. We'll have to talk about when the lab might be able to be open. We can have 5 people or maybe 10 people.
4 or 5 that we can run at a time.
Yeah, for sure, at a time. And maybe if you're alternating pieces, so one person forges and then you put it back in and the other person's forging while your piece is heating. And then we have some people that maybe want to do some cooking. And we're not eating in the lab at all. So, we'll also do some induction furnace cooking. So,
Sounds like it's worth sticking around for to me.
yeah.
Yeah. All right, so
So
we'll stop there for
you
today.
want to stop there then?
I think we should, I mean, I could keep going, but I don't want to cut too much into the
Yeah,
lab
I think
time.
we're going to have trouble finishing up. So,
Yeah.
what I'm going to try to do, guys, is I'm going to try to take the PowerPoints and then assemble them the way they actually are in our lectures here and the way the videos correspond to them. And then when you go on to Canvas, the PowerPoint you're looking at should correspond to the video, even though it'll be kind of like a little disjointed.
A little bit, but it won't be too bad.
But, okay, so let's pack up. And any other questions on this?
Before we leave, there's a homework assignment, which Dr. Metzloff is going to put a steelmaking video on Canvas, which I've got to make sure you get before today. I'd like you to watch that because it'll cover steel making in more detail than what I touched on. I really focused on the solidification of the ingots and then how that affects us as forging, but I think it's worthwhile to have a pretty solid understanding of the steel making process as well.
Also, there is a little paragraph you're supposed to do on Viking sword. I made that due for like Tuesday or something like that because didn't get the Monday. Okay, good. And then so we'll do something similar on the steel making video. That'll be the homework.
Does quiz 2 correlate to that homework?
No, quiz 2 is not going to happen. It's just watch those other videos.
Oh, okay.
I didn't get around to. I'm trying to develop 5 classes on Canvas at once, so it's not going so well. Alyssa, let's hold on 1 second here. I think I might be able to get her on the phone. She wants to tell you what's going on. She's packing up to do some presentation right now. I don't know if you know who she is. Alyssa Toninato is a fairly famous artist. One of her most famous pieces, she did the whole United States in frying pans. And it's like the size of this wall. Like, you know, Texas is about this big. And so she was on Martha Stewart, she's been on the Chew if you follow her in the food shows and stuff like that. And she's always on TV and stuff like that. She's really dynamic and fun to work with. I've been working with her for about 8 or 10 years now. And when I first started working with her, the gating systems were all terrible. She's got like 50-60% scrap on her front end and all that kind of stuff. And so we're trying, you know, she's an artist, so she just thinks differently, but we've got her kind of measuring temperature and doing, you know, things that increase the chances of that to come out. So I'll go quick to see if she'll answer here, otherwise we'll just go downstairs. I have a flyer that I'll put on Canvas and send you by email as well. But essentially, where is it? I think it's got it by text. There you go. Okay, so we're gonna start pouring. Typically, first half both in the ironette tube, and that's a bunch of artists, so time is kind of a variable that usually tends towards the later time. But so what a cupola furnace is essentially a blast furnace.
Yep.
That you put already reduced iron into. So you're putting chunks of iron in the top. They actually literally break up bathtubs and take that, and they actually chip all of this, the ceramic stuff off of them. If you want to help with that, they love it. It's actually really, it's kind of like forging. It's really, you know, get out aggressions and all the homework stuff and yeah. So anyway, that's probably happening next week sometime during the week. And then, so it says 11 a.m. to 7 p.m. sand carving on that must be the night before or something like that. You guys could make some molds and take them down there. If you're helping out, she usually does. Is it
I
not?
don't know if our resin climate sampling works right now.
What's wrong with it?
Something with the resin.
This is not curing or what?
It's not coming out. The pump is kind of problematic, but it's not.
Okay, we'll have to take a look at that. We could make some molds if that's working. If not, they have these little heart molds there. You do have to pay for them, and you kind of scratch in, you know, I like someone, whatever the heck you want to put on there. And then they just pour it open. If we could make some little chunks of sand, you can carve whatever you want into, but you just have to think about it, it's backwards. So lettering is backwards, okay? So what you do is you draw it on a piece of paper with a black magic marker, then you flip it over and you draw it on the other side because you can see through the paper, and that's what you draw. That's an easy way to get that sorted. So let me just see if she's available. I can't guarantee, but she has to have a mouth. She's loading up her truck to go over to some.
Alright, do you feel like I'm putting this piece of stuff?
Hey, listen, Kyle here. We got my students listening to you, so, you know.
Hey, awesome. Keep it clean.
Yeah.
Keep it clean? Okay.
Hey, just want to tell them quick, get them going and see if you want to give them a little pep talk about getting out to your place.
Sure, yeah. So we're going to be melting metal in the parking lot in 6 days, 7 days. And what we do basically is we start early in the morning. We set up the 4th floor. There's going to be a bunch of artists all over the Midwest to help the students. People bring molds in, and there are a lot of people from the community making molds. And so lots of jobs to do. We're going to be breaking iron and coke and weighing out charges, setting up the 4th floor, and building up the furnace, and there'll be a scratch mold workshop happening inside the big warehouse area that we have. It's a new location for us here, which is really awesome because it's a nightclub actually here in Madison, and it's pretty sweet. It's an industrial area. We have 6,000 square feet inside of the warehouse where there'll be an iron gallery to show people like what the artists actually make, as well as an opportunity to make stuff that day. So basically, like, you know, kind of a year cap, how we work with Platteville, and people think you guys can come with.
Oh, this is the Madison folks too.
Oh, you're Madison too, okay,
Yeah.
right. So if anybody that's here and wants to be part of kind of the 4th floor activities, we're open to that. Basically, have liability waivers, obviously, and then kind of need to know a little bit about your experience so that we kind of know how to place you. There is some liability, and there's outside, been a lot of snow, going to be getting warm and getting icy
That's a small hand label. We might have a couple of them here that we can bring along.
Yeah, okay, great. Yeah, we have 4 of them here. I think there's 4 or 5 of them. I think there's 3 smaller ones that are like number 6s, and then I have a number 8. And, I think they hold like 30 and 40 pounds or something like that. They're not too bad. They're nice for these little scratchable, they're not too much metal. We're actually using your label scan. Oh, sorry.
That's okay.
You want to take that back or before?
Yeah.
But it, so we have a big label that we use, so it's the one we use a lot, for the smaller stuff, so we have to do that. We also will join by the small arts and artists from Milwaukee here, my alma mater, from my end, Milwaukee, for art design. There's going to be 25 sophomores, the very first iron form, the very first handle, spring game from Milwaukee, Madison, so there's a lot of people new on the 4th quarter here, so it's really great to have, and we have a rich mix of people that have a lot of experience and people that are really brand new to this. So we keep it up, just like kind of how we organize it. We have teams of 5 usually. We have 2 people on the ladle, the ladle, and the spinner, and then someone on the shovel, and then, people to the shovel, I don't know, it's kind of nice. We have just kind of a group of people together, so, sort of that means you as far as how, experienced you are, how tall you are, it also helps.
What time do you think would be a good time for people from Madison? Some of them have some pouring experience, some of them might want to do like a little, shadow someone for a while, for sure, at first, but,
Yeah, the event technically kicks off at 11. We will be there at 8 in the morning, set up. So if you are a Rory person, you want to set up with us, cool. We'll be stuff out, pork truck, moving pallets out and kind of like stuff. We'll learn how to like set a furnace, and sort of that stuff. We got like a crew of people doing that, so you can kind of be part of that.
is Kelly coming?
Kelly is coming. Yep, and Kelly's coming, and there's gonna be Glenn, and I've got, the whole crew of people from Chicago, who is great. Who's from, Andrew from Milwaukee, of course, we've got, Rocky Hampton and, Mike Everly, they're from Madison here, there's Gordon that do iron. There's
I told Peter about it, Peter Flannery.
Oh, yeah, okay. Yeah, that'd be pretty sweet to see him. I've seen him a long time. And, David Winter.
Good.
It's a fun day. He's got a silver input, nurse and a silver surgery, so.
Okay.
We'll enjoy it, but, knows about it. Yeah, but then otherwise, if you're like kind of on the later in the day, I would like.
You pour till what, like about 5 or something like that?
Yeah, it's kind of nice to be there around like no later than 1. So
Okay.
if you have a big stock, and I like talking.
Great, safety stuff, yeah.
With all that, yeah, if you're like just gonna jump in and expect to kind of like be doing something, it's gonna be harder for me because we'll have already organized kind of what's going
Yeah.
on.
Okay, so we'll try to be there just before 1 then.
Yeah, like noon,
Okay.
is nice.
Okay.
It's nice. You don't have to be there right when it starts, but you want to bring.
Okay.
Otherwise, yeah.
Can you tell us a little bit about the venue that you're at, let's say afterwards?
Yeah, afterwards. So this venue is a nightclub, and it's a full bar on site. So there's already going to be a DJ from Chicago that's going to be playing. It's a separate team from this event, but it happens to be rolling right into the same time. So if people want to hang out with that, that's what our crew is going to do. We're probably going to hit the bar right away, and then go in the dance floor. We have
That sounds dangerous.
I don't know. You have to look up on the thing. I don't know the guy. Like that's playing, but it's like it's very industrial kind of like very.
Okay. And so, who's the beer sponsor?
So we don't have a beer sponsor this year because it's a full bar.
Okay.
Like, however, we do have something very special from the really awesome company called Miss Mary's Bloody Memorial Liquor, and they are based on the Milwaukee. They have donated a whole bunch of Bloody Mary, Lake
can we grab some molds?
We haven't started this yet. I'm trying to see like a whole bunch of yeah, I've got 3 volts or
Okay.
so much stuff.
Yeah, I don't know that we can get a machine running, so just, I'll let you know after what the deal is. We'll see you later on, right?
Yeah, dude. Yeah, I'm gonna stop by later. That's great.
Okay.
I'll call you after I get done with the adult website, but, yeah, it's like, what's the last thing I'm gonna say? Oh, yeah, food trucks will also be on things.
Okay, yeah.
You know, this is the food fire system, and then we'll go there.
Man.
So, yeah, he's like Caribbean, so I think that's gonna happen. It's nothing personal.
Okay. Well, I'll try to get the Platteville folks all sorted out too, and we're gonna go punt on some metal. We got a 14 class. We got a bunch of students who want to go punt on metal, so we're gonna head down there, and we'll hopefully see you soon.
Hey, that's awesome, man. Yeah, well, thank you so much for letting everyone. I just sent you a link to the poster.
Yeah, I'll put that poster on our website. Yeah.
Okay, great. Yeah, there's also a Facebook event, so there's been multiple description there about like what's going
On
on.
Facebook, on your Facebook, or which one?
Yeah, you can go to Beeline and under the event section there, but you can just go to type in 2019 and pour your heart out.
Okay.
Here and then pour your heart out and feel affected.
Sounds
And
good.
they'll send you a small itinerary out there of like what is the effect and I keep it going till we're done. So I've got,
Okay.
I think I've got around 22. I feel like
I got a bunch of stuff I bought, but I thought it was kind of neat looking, it was cool, kind of handy to have for taking nails on your wall, you want to look at a picture or whatever. It's not anything so large as a big pry bar, but so this is about 1/2 inch diameter as a starting stop, and the first step is to forge this taper out here. Now this one has got kind of comes to the point that Dr. Metzloff said you could make that a different shape if you wanted to. I'm going to make mine as like a model of this just because I kind of like the way it looks. So the first step is to forge a taper. This taper is a little bit of a gradual taper. So we'll do that first.
Oh, you're using this one?
Yeah, because actually it's hotter than mine. So yeah, so we're going to go this one. We'll just let mine keep running. So I showed forging a taper last week. You take your workpiece, you hold it at a slight angle, you tilt your hammer at a slight angle, and when you hit it, so at this point, the goal is just to make a nice square taper. I'm going to make this one just a little bit longer. So I'll take one more heat to make it square, to lengthen that square section. After that, we'll show how to make it round. Now the stock that we have to start with is octagon. There's no particular significance to that. It's just what I had forged at home. It's faster to make an octagon than to make a round. And if you're going to be forging for something else, then an octagon is fine. And it looks kind of nice. So are there any questions over how I did that? I know it went kind of fast. Any questions on how that
You made
gets
it
done?
square, right? It was square.
It was square. I made it square, and you're just trying to keep it a nice uniform square. You hit it pretty hard. You don't have to hit it super hard because it's not that big, and as long as it's hot, it'll move pretty easily. Find a hammer that you're comfortable with. I've got several that I brought that you guys can keep here in the lab. I've got some others that you're welcome to use that I'll collect tonight when we go home. They're different sizes, different handle shapes. You find something that fits you, yeah.
So when you're
And at one point there, you saw I was kind of just giving it one blow and then flipping. So it just depends on where you're at. When you're at a larger cross section, you can give a few more blows before you flip it. So I'm still going to, in this heat, I'm still going to keep it square. I'm just going to make the taper a little longer, which means I'm going to work back up towards this section that's still a little bit thick yet. Now that I'm not working on the point, I can work right on the main face of the ankles, no problem at all. So what I'm looking at is the spread on the sides. I can't really tell what's going on in this plane because I'm looking straight down, so I can't really see what's going on. So I'm looking at the spread. When I see that it's doing something I don't want, then I rotate it and hit where I need to hit it to make it go where I want it to go.
It's harder than it looks because if you don't turn it exactly 90 degrees or close, you get a parallelogram. And it's hard to straighten that back out.
That's true. That's true. So here's what we have. Nice and square. And what we're making here, if you make a parallelogram, okay, it's not the end of the world. This is a pretty straightforward, pretty simple project, very forgiving. So if you make a mistake, that's okay. Just keep going. So now I'm going to reheat it and I'll make it round. But when you make a square into a round, you have to first form an octagon. So what I'll do is I'll take the corners that I just created and I will orient them vertically. I'll hit along the corners. I don't need to hit super hard. A little harder where it's thicker, a little lighter where it's thin. And I'll push the corners in and then I'll rotate 90 degrees to the other set of corners. Work back and forth until I have a nice octagon. And then in this case, since I want a round cross section, I'll go back and I'll hit the little corners and I'll rotate the stock while I'm doing that and it'll be round. But I might be able to get all that done in one heat. It might take two. We'll see. Any questions so far? Any questions about anything else that you just want to ask me? Not related to forging, but engineering, metallurgy, working in industry, getting a job, interviewing, anything?
Yeah, that's... What year are people are? There's no freshmen in here, obviously. But what about juniors and seniors? Juniors? 0 seniors?
Alex is graduating.
Okay. Now, what's the reason? Was that the prerequisites? Why there's no, or there's people don't have their crap together before they get to this year? Oh crap! I got to get a job. I should learn something.
All right. So making an octagon and then making it into a round. And sometimes you'll go on the corners, several passes before you are ready to make it round. And that's okay. That's what I'm doing here because I want it to stay even. I don't want to just overpower it, just smash it in one dimension. I want it to be even all the way along its length. Now I will go ahead and make it round. There's enough heating there to do that, even though the tip is flat. For this project, that's okay.
So it's 0.3% carbon, so not super hardenable.
Yeah, if this was a different alloy, doing this might cause it to break. But with your lower alloy steel, you can get away with this kind of thing. I'm also not hitting it real hard right now because all I'm trying to do is make the surface smooth. Okay, so start over here. end for end so that I can make the nail puller work. So to do that, I actually need to switch tongs. So I've got a collection of tongs over here for holding smaller cross sections. No, you won't hurt it. We'll just oxidize a little bit more as well. There's one that fell down in off the brick down there. So we might want to fish that out and get it up on the brick or put it in my furnace over here. I'm going to go ahead and put this pair of tongs in the water just because the end is hot and that way it's safe. Nobody picks up anything that will hurt you. So the next side is going to just be a flat taper instead of a round taper. So we'll forge out, and it doesn't need to be as long as this one is. We'll forge out a flat taper, just a little bit of length, and then we're going to use a chisel, and we're going to split from one side only to create the notch that will grab the head of the nail. And then we'll have to curl that over to give it a little curvature. You can just set it up on the bridge. Just someplace where someone can get at it. And while they're doing that, this is hot enough for me to work, so I'm just going to grab this. And because I made it round, it doesn't matter how I orient this for making the next side. I'm going to just flip it 180 degrees to try to keep the paper even on both sides. So I have to hit it harder. Look, it's getting cold. Now, I'm going to reheat this. I'm going to flatten it out a little bit more, and then I will actually stand it up on edge and work the edges a little bit, just to provide a uniform dimension. I'm not trying to make it very narrow, but when you spread metal in one direction, it tends to be kind of uneven and wavy along the edges. I want that to be a more clean look, so I'm going to just tap the edges a little bit. The girls last week was talking about the crazy things. That's going to be a much lower temperature. Where you can stand on the edge. But you've got some aspiration. You can still do it. Yeah. Taper this out a little more. Up a little bit. It's okay for it to be tapered in this dimension. I just want it to be kind of flat and clean looking. Alright, so the next step is going to be to split it. We'll need a helper for that. So let me talk quickly about anvils real fast. An anvil has a hardened steel face, and so you don't want to, there's certain things you don't want to do on the face of an anvil, one of which is cut. It's okay to start a cut, but you don't want to finish a cut on the face of an anvil and drive the cutting tool into the face because you'll mar the face. The faces on anvils are quite hard and it's difficult to get those marks out. Fortunately, most anvils are set up with a soft spot right here. This is the place that's intended to be used in that fashion. So you can finish your cuts over here, and then if you happen to go all the way through, it's a little bit hard and soft. It's a lot softer there. Won't be a problem. And if you ever needed to, say, do a weld repair or something over here, it's easy to do that. So on this anvil that I have here with the two horns, I'll point out that this spot here is actually a section in this corner where the face actually has a steel base on a wrought iron body, and the steel base broke away. So this underneath is soft, no forge here. I'm working I'm going to have you just hold these tools are called hot cuts here. They look like hammers, but they're really odd ends, but they're intended to be struck by a hammer, so you hold this on the work and then strike the edge and drive it through. So, Alex, I'm going to have you hold that for me. Actually, you know what? What I'll do is I'll actually have you hold the work and I'll hold it. I'll get it out and then I'll hold the cutting tool. And you don't have to go in real far because it's not a really big tool. You want to try to just, by eye, get it in the center. Hit it once and check it, make sure it's where you want it. If you need to get a little more length, go ahead and do that at this time. Now, these tools have a bit of a radius, so you have to kind of tilt them up a little bit to get this top corner to go all the way through the workpiece. So I'm tipping that up, driving it through, and we're through on the front, not quite on the back, so I'm going to give that one more blow, and there it is. So now I'll reheat it so I can do the bending. So I've got my Alex tray here. Let me show you all the options. So I just throw that thing out. Right there. This is the file that I have off. So what we're going to do next is bending operation. We need to bend this so that we have some leverage we actually use. So we're going to heat that and bend it. And I'm not going to bend it over the horn. I could, but I don't need to. So I'm going to just use the edge of the anvil right here. This anvil is really nice. It's got a nice radius right here. You can use the horn. You can use the edges on the anvil. There's a steel block over there. I brought a steel block. I had it, and I wanted to show everyone that we can be very effective in making things with very simple block of metal, like I was talking about last week. Now it's quite thin, so it's going to heat up quickly, and we're hot. Because our metal is small, something to pay attention to, we want to curl this in so that the direction that we drove, now we're curling up into that. So I'm going to start by just being on the very edge of the anvil, hitting both sides at the same time, and slowly moving forward, and just kind of pounding them around. We're almost there. It needs a little bit more. When you are bending, you don't hit down on the anvil, you hit off of the anvil, and the edge of the anvil becomes your fulcrum for the bend. Now it's just a matter of deciding how much bend you need. I think this one probably needs a little bit more. I'm not sure where our example piece went. Over here. So we don't have to match that exactly, but I'm close, but I think I'd like to get just a little bit more out of it. Not much, just a little bit. That'll give me just a little more leverage if I have a stubborn nail. Now, this metal is not very thick, and it's not a high alloy, so when it's at temperature, it's pretty soft. And since, of course, we flattened it out, it bends pretty easily. So you don't have to wail away on this. You might have noticed that the blows I'm delivering are mostly with my wrist and elbow. I'm not giving real big shoulder blows in most of this work. Also, because it's small, it heats up really quick. So, you know, just because we have a lot of people around tonight, pay attention to your work and take it out when it's hot. Don't let it sit there longer than it needs to, just because we're trying to get everybody through. Now, if you want to bend beyond 90 degrees, you can actually flip the workpiece up and hammer this way and get yourself a little bit of a curl going. Now, the only thing I'm not real happy about is where I split is kind of dipped in. I don't really like that. So I will hook this right over the very edge of the horn to just even that out a little bit. I can work there, and there it is. And that will need a little bit of file work to open the slot because it's closed up as I bent it, but That's a pretty simple thing to do, won't take long at all. So there's one other step, and that's to bend the opposite side. So I'm going to reverse the position on the tongs and put the piece back in the furnace. I don't even need to get it all the way in the furnace, really. And it won't take too long to get hot. And here, in my case, since I've got a cylindrical cross section, I'll go ahead and bend that part over the horn. And then it'll be done. So something to think about would be, what, if any, kind of heat treatment would be appropriate for this tool in this size and this alloy. We haven't gotten there in class yet, but you may have been given such questions in some of your other courses. Off the top, in my case here, I'm going to bend this in the opposite direction that I bent the little nail pulling section, so I find a spot on the horn that I kind of like from a curvature standpoint. Start at the edge, just feed it forward a little bit while I hit. I can follow it around with my hammer if I need to. I'm going to come over here. I'm going to give it just a little bit more of a curve on the tip. And there it is. As far as I'm concerned, this is done. What I'm going to do with this, I'm going to set it down at the bottom of the forge stand there. That way, no one will engage with it quickly and hurt.
Why don't you just punch it?
Why not? Why might I not want to do that? Got it? Did you have that happen? Gets back to the understanding of the material you're working with in the processing. This is kind of the whole point of our class. The material, we forged it, but once we get done forging something, what are we going to do with it after that? Of course, we have more lectures on that, but that's a really important part of metallurgy. You do a shaping operation, and then you do a heat treatment operation. So what kind of heat treatment do we do, and why? Think about that for a while, and then we'll talk about it. But now I'm done, so somebody else needs to get up work, and there's enough metal here for 4 people. We've got enough metal and tools for 4 people to be working at once. Dr. Metzloff's done plenty of blacksmithing. I know he can coach people. I can coach people. So get in and work. There's a pair of tongs that will hold this size metal at every anvil, or there should be.